Okay, end of the week and almost the end of the course. Just 3 more sections after this. So what does the Laplace transform have to do with solving equations? Okay, so for an integral transform to be useful, you need an inverse. So typically what you do, you have your problem. You move it from the T domain to the S domain. You can do stuff there, come up, find things, whatever. But then you've got to take that back to the T domain. For that, you need an inverse transform. And so you might worry about uniqueness because, for example, we know with antiderivatives, there's no uniqueness there. So anyway, so if a function little f has a Laplace transform big F, it's called the inverse Laplace transform of big F, and we denote it by L inverse of big F. Lurch's theorem says that we do have uniqueness. For any continuous function of exponential order, L inverse of L gives us back where we started from, as long as we stick with continuous functions. So it's unique up to points of discontinuity, and of course, we can't, that's always going to be a problem because, if you've got a discontinuity in your function, you integrate it, it's going to kind of ignore the point of discontinuity. So you've got uniqueness, and you also got linearity, and that's the standard way that you prove things. So you look at the inverse transform of a linear combination of things. Well, since they were Laplace transforms, you can write them as Laplace transforms of some function, and then you use linearity of the Laplace transform, and then you've got your L inverse against L. Then you can use uniqueness to get rid of that, and you're just left with A little f plus B little g, but little f is the inverse of big F, and little g is the inverse of big G, and there's your linearity for you. So let's have a look at some examples. So 2 over s plus 3. Well, we know the inverse Laplace transform of 1 over s plus 3 is e to the minus 3t. So by linearity, we've got that the function is 2 times e to the minus 3t. And number 2, we use uniqueness and linearity to write 2 over s. The inverse Laplace transform that is 2. 3 over 3 plus 3 over s plus 5 is 3 times the inverse transform of 1 over s plus 5, which is e to the minus 5t. Here's a little bit more complicated one. We've got s squared plus 9 on the bottom. So we cut it up into s and to 3 because we know the inverse transform of those is going to be cosine and sine, and that's what we get. Okay, so the first module question is find the inverse Laplace transform that big F there, right there. Okay, so let's use it to solve an equation. So let's first do a first order equation. 2x prime plus 5x equals e to the minus t, x0 equals 1. So remember, when you use Laplace transforms, you basically need a inverse value problem. So we've got an equation, so 2 things that are equal, so their Laplace transforms are going to be equal. So we take the Laplace transforms of both sides, and we use the linearity, okay, and we plug in the initial value there, x naught, and we end up, so we put all the terms with x, big X, right, the Laplace transform of little x on one side, so that's 2s plus 5 times big X equals 2, which was, remember that was 2 times the initial value. plus 1 over s plus 1, which was the Laplace transform of e to the minus t. And so we put that all together, we solve for big X, and we get 2s plus 3 as the numerator divided by s plus 1 times 2s plus 5. And we'll get into this in a little bit, but that's actually the same thing as 1/3 over s plus 1 plus 1/2 4/3 of s plus 2.5. So using the inverse transform, we get the solution as 1/3 e to the minus t plus 2/3 e to the minus 2/5 t. And let's just check that that works, right? Plugging in t equals 0, we get 1/3 plus 2/3 is 1. 1/3 of e to the minus t is the particular solution, right? And we can see that because when we plug it in there, we get 5/3 minus 2/3, right? Because when we take the derivative, down comes the minus 1. And the 2/3 e to the minus 2.5t, that's the homogeneous solution, right? Because if we plug that in, e to the minus 2.5t, if we plug that into 2x prime plus 5x, that will clearly get 0. So it's worked. So the big question was in that line going from 2s plus 3, we had a rational function and we split it up into its partial fractions. So you might remember that from Calc 2 when you did integration. And so just to remind you how to do partial fraction expansions. So first you put it in as a proper rational function. So you want the degree of the numerator to be less than the degree of the denominator. Otherwise you can just divide through and you get a polynomial plus that. So over the reals, you can factor any polynomial, remember, into linear factors and irreducible quadratic factors. I've written my irreducible quadratic factors as s plus b squared plus c squared. So just sort of completed the square, and you can see that that is, in fact, irreducible. Now, for each linear factor, s minus a to the m, in the partial expansion, you're going to get m terms. So you're going to get a1 over each progressive increasing power of s minus a. And for each irreducible quadratic factor, the irreducible factor to the power n, you're going to get n terms, right? And so since it's order 2, you're going to get, in each term, you're going to get 2 unknowns, 2 degrees of freedom. Some people like to write it as b1 times s plus c1. I prefer to do it that way because then it's already in the form to use. You might remember this from when you did integration, right? Because if you write it in this form, it's all ready for the substitution. And so now you've got to find the A's, the B's, and the C's. So typically what you do is you put it back, you write out your partial fractions, you find the common denominator, which is going to be QS, and then you're going to have a relation between the numerators between the two sides. On one side you've got the A, B's, and C's, and the other side you've got PS. You've got your P, and you just do it for each coefficient, right? 2 polynomials are equal if and only if their coefficients are equal. And you go through and you've got a system of equations to solve. Okay, that should come as no surprise, right? Because we've been solving linear systems of equations all the way through this course. So for simple problems, you can actually do this by hand, that's okay. For complicated problems, there's a nice partial fraction calculator in Wolfram Alpha, but there's lots of others. You just do a Google search, but Wolfram Alpha is nice, and that should even work on your phone. Okay, so for example, here is a partial fraction, 2 over s to the 4th plus 2s cubed plus 2s squared. Okay, we factored that out. We can pull out an s squared, and we're left with s squared plus 2s plus 2. That's an irreducible, so I'm going to write that as s plus 1 squared plus 1. Okay, so I'm going to have, it's a degree 4, right? So I need to solve for 4 coefficients. I'm going to have an a1 over s plus an a2 over s squared plus a b times s plus 1 plus c. I bring it together, and I get that sort of complicated expression there in the numerator, and I get back in the denominator, I get what I started with. And so now we just go through power by power. So if you look at that numerator, what's the constant term? Well, the constant term only turns up in A2, right? Because in A1 and the B's and the C's, we're multiplying by an S. So we've got 2 equals 2A2. So straight away we can see that A2 is 1. We look at the linear term and we get something from A1 and something from A2. We don't get anything from the B's and the C's because we're multiplying that by S squared. So we get 2A1 and 2A2. And that has to equal 0 because there's no linear term on the NP. And so since A2 is 1, A1 has to be negative 1. Then you'd likewise do an expression for s squared and s cubed. The simplest one then to do is look at the s cubed one, because you've got a1 plus b has to equal the s cubed term, which is 0. Since a1 is negative 1, that tells us that b is 1. And then you go back to the s squared term and you see that c has to be 0. And so that's the partial fraction composition right there. And so straight away I can read that off. Minus 1 on s, the inverse transform of that is minus 1. The inverse transform of 1 on s squared is t. Oh, and we haven't, that's going to be the next module, what the inverse transform of that is. But you can kind of see that it's kind of like a cosine t. It actually turns out that it's e to the minus t times cosine t. So that's why I like to write it like that, because it's kind of obvious what it is. But just hold on to that thought. We'll see that next module. Here's a much more standard one that you've probably seen. You did things probably like this when you did Calc 2, when you did integration. So we've got s plus 5 divided by 3 linear factors, right? So we write it out as a coefficient divided by each linear factor, put it together again, and you see that it has a nice form. And so that means the numerators must be equal. And in this case, instead of just comparing coefficients, since they're equal, I can plug in s equals minus 1, and you see that the b terms and the c terms drop out because they're multiplied by s plus 1. And so we see that we get a times 3 equals 4. So that means a is 4/3. Plug in s equals minus 2, and the a and the c terms drop out, and we see that minus 2b equals 3. So b is minus 3/2, and similarly for c, we get c is 1/6. And so straight away we can write down what the inverse transform is. Okay, so let's finish off by looking at a second order equation. Okay, and we've got initial values. They're quite nice initial values because they're all 0, so that's not going to add anything to our, when we take our Laplace transform. So again, we take the Laplace transform on each side, and we end up with s squared plus 3s plus 2 times x. And hopefully you've noticed by now that that's the characteristic polynomial of the equation. So it had to be somewhere. There it is. Equals 4 divided by s plus 3, because that's the Laplace transform of e to the minus 3t. S squared plus 3s plus 2 is equal to s plus 2 times s plus 1. And so again, we've got something divided by 3 linear factors. We do the partial expansion. I do the same thing as before. I look at the numerators when I combine them. And so I can plug in -1, -2, and -3. So for example, if I plug in -1, we see that A is 2. Plug in -2, we see that B is -4. And plug in -3, and you see that C is 2. And that gives you the solution. And again, you can kind of tell that it is the solution, right? Because we plug in 0, we're going to get 2 minus 4 plus 2 is 0. Take the derivative, we get -2 plus 8 minus 6. Again, that's 0. 2e to the minus 3t is the particular solution, right? And e to the 2e to the minus t minus 4e to the minus 2t was the homogeneous solution. So everything works out as per usual, as you would have done if you'd done the method that we've done. So this is like the third different method that you've learned to solve these equations. And so your question, last module question is, solve with Laplace transforms x prime plus 3x equals 2 with x0 equals -2. Okay, see you next week.